I'm Ricky Sethi, and I also want to thank Eric and Jackie and all of our colleagues for kindly being here. This is my first sort of book launch, so I wasn't exactly sure what to talk about, and Eric sort of said, talk about whatever, place the context for this thing and whatnot. And I thought maybe a good context might be people who saw the book might be confused, who's this guy that's talking about it? And the reason is the picture that I chose for that I use on the book and the website is from my wedding, which is now like 12. My wife will kill me. 12. I'll stick with 12, 12 years ago or so. And one of the few things that I've learned in my life is that once you take a good picture, hang on to it, because people like me definitely need it. So that's the one that I plaster everywhere. But the book itself is called Essential Computational Thinking. And it says sort of in the subtitle what it's going for. I'm trying to build up this idea of computer science from scratch. It's not a rigorous derivation. It's very highly mathematical, though. But it's not rigorous in the sense that I can't do it from first principles alone. But my background tends to be, my undergrad was in physics and neurobiology and English. And then my master's was in business and physics. And then my PhD was in computer science. So I build upon a lot of the stuff that I have that I started working on. And one of the core ideas that I found is that computer science, for the way that I build it up in the text as well, is sort of a superset of physics. If you think of like math, for some reason, nature tends to speak this odd language of math. We don't know why, there's the unreasonableness of why math describes nature, but nature tends to speak math. And so all of the stuff, if you're a reductionist, you might look at stuff in physics and you see that all of the things in physics, all of the equations in physics, it turns out, are computable functions. So what exactly does that mean? This is what sort of mathematicians around the turn of the last century started to struggle with. And so people like Turing and von Neumann started to answer this question. And they started to talk about what it means to be able to compute the answer to a function. And so this led to the idea of computable functions, and Turing machines or algorithms were a way to sort of categorize that. And so it turns out that every single function in physics is computable. Every single thing in physics is computable. And this nascent science that started to arise, computer science, which started to deal with figuring out what functions are computable and what are not, started to sort of serve as a boundary between what's physically known to be realizable, and what's just weird math stuff. Right. So there's a lot of stuff in math. Mathematicians are much smarter than me, so I don't understand all their math, but we do understand those mathematical ideas that we can apply to physics. And computer science sort of sits at the boundary and tells you which functions in math are computable, so that they either are already applicable to nature and physical reality or might in the future be so. I mean, there are these examples that we use all the time. We know that we live in sort of a Euclidean space, right? Or all of our math that we started to do, the initial geometry that we start to do, it's like the Euclidean geometry. And there's a couple of mathematicians that sat around in the early 19th century and started to think about, well, what does geometry look like on curved surfaces, right? Like the Earth that we live on. And we don't deal with these Euclidean spaces at these higher levels. And they came up with a whole math to describe curved geometry on curved surfaces, which was very cool, but no one really cared. There wasn't anything to do with it. It wasn't until about 70 years later when this obscure patent clerk in a Swiss patent office, Einstein, was starting to take his theory of special relativity and then extend it to general relativity and see what happens under accelerations, that he realized space-time itself is curved. And so he needed a mathematics to describe this curved space-time. And they'd happened to come up with it already. And so his old teacher, Minkowski, said, dude, this stuff has been done already. And so they started to apply this math. So mathematical ideas come up, but we don't always immediately realize they're applicable to nature. When we do, usually they end up being very helpful. So computer science helps us figure out, from a theoretical perspective, what mathematical functions are computable or not. And so that's the way that I sort of placed this book. It's a textbook. I went with Cognella Academic Publishing for it. One of the reasons I went with that is so that it would be, I could put a copy of it for free for students to use. So if you go to ResearchGate, it's freely available. People can look at the whole book. So, you know, students and all don't need to buy the crazy expensive. I agree completely with Ben. These things are way overpriced, and I love OERs. I started to get into OERs after I'd committed to this, but with one of the reasons I went with that is so we could make sure that it would be publicly available for free forever, so people can get to this. But the whole idea of this was starting off with, because computer science is a real science, you could argue other physicists and digital physics also builds up this idea that the underlying nature of physical existence isn't particulate. It's not even fields, right? We know, okay, so there's this standard model, and you've got things like quarks, leptons, and intermediate gauge bosons. And then we say, okay, let's go to quantum field theory and talk about this idea that these particles aren't really particles, they're fluctuations in these fields, in these quantum fields. And it actually goes further than that, where in digital physics and now in quantum information theory, we start to talk about the idea that the fundamental nature of existence isn't particulate, but informational. And this idea of information theory came out of computer science in a way, in a central way, because Claude Shannon started to deal with this also in the 1940s, same time that Turing was doing it. Von Neumann, it turned out, had already sort of looked at this in a way. He started to develop a quantum entropy. And so he was on the way to developing a quantum information theory. But Claude Shannon, who was sitting around at AT&T, right, and at that time in the 40s, AT&T had this cool thing where they said, it's sort of like what the model that Google has adopted to some extent now, where it said, okay, you guys sit around and do the stuff that we pay you for 70% of the time, 30% of the time, do whatever you want. So Shannon was sitting there and he was helping the military effort, et cetera, 70% of the time. But 30% of the time, he went off thinking about what is it that AT&T is in the business of. And at that time, this is, you know, telephone and telegraph. And he started to think about the idea of data and information and what information was. And so he started to quantify the idea of information. And thus was born information theory. The reason I talk about this is because this is the stuff that underlies the text. So I build up the idea of computer science as a real science. And the most consistent definition of a science that I have is the one that it makes predictions. That's all it does. Everything else is all very nice, and explaining nature and all this other stuff is very nice, secondary and secondary to the main gist of what a science does, which is make quantitative, precise predictions, which are then testable. And so there are people that sort of also reflect this, people like Feynman, who talks about, experimentation as being the key to science and stuff like that. But in order to make these predictions, you need sort of an idea of a math that underlies it, because you're going to make some kind of model. And so the book builds upon this idea of how science works, what science is about, predictions. How does it work? Well, in the past, you might have said it had this idea of a scientific method, right? Everyone knows it's not an actual, thing that you shoehorn your approach into, this thing of make a hypothesis test and all that. It's a way of thinking about a problem. And so as computer science developed and these ideas of information theory and quantum information theory developed, we realized that computer science, sitting at sort of the boundary between math and physics, was sort of extending the idea of physics. So modern physics is a lot about information. Wheeler, this eminent physicist, right, who always had a way with words, when he was describing general relativity, he said, space tells matter how to move and matter tells space how to bend, which sort of encapsulates it very nicely. He had another one of these nice little encapsulations where he said, it from bit, which implies that the fundamental nature of existence is informational. And so we talk about the information content of black holes, for example, and we talk about the holographic universe as being the informational content of the universe that we utilize. So in all of these, this approach of using that scientific method has started to sort of expand. And what I would say that it has expanded into is this idea of computational thinking, because in the end, All of physics is about dealing with computable functions. That's all that physics is. All of physics is computable functions. So how do you define computation? How do you go about it? Well, you take this approach of computational thinking, which in a sense would be a generalization of the scientific method, and sort of encapsulate some of those heuristics which would help you. It's not some method that you have to force yourself to do and you got to say, check, step one, check step two. Great, I've now done science. It's not one of those things, but these are heuristics that might help you in thinking about and solving a problem, a formalization of the logical approach from Aristotelian syllogistic logic all the way down to this idea of computational thinking. And so this is what the book builds up. In the first 3 chapters, I go through sort of this history and building up information theory and talking about what that is and Turing machines. Then we shift gears in the second part where it's all about programming, and we switch and say, okay, now that you know some of these ideas about how to approach scientific problems, how do you actually then get some computing agent to do it? In the past, the computing agents were humans, right? All computation was done with humans. When Feynman was in the Manhattan Project and, he bragged about, we have the latest computers, what he meant was the female mathematicians that were sitting there solving these problems. We were the computers. The digital machines became our computing agents of choice over the years because they happen to be fast, not very smart, but very fast and very accurate. But anyway, so this idea of these digital computing agents being used is also essential in science nowadays, especially with the rise of big data, as probably you guys are aware. In the year, like I think it's 2009, we created as a human species more data than in our collective history, cumulative collective history up to that point. So if you say 50,000 years till behavioral modernity, not like the 200,000 years for Homo sapiens, but say 50,000 years to behavioral modernity to now, cumulatively in that 1 year, we created more data than we did in our entire human history. And each year subsequent to that, we've created more and more data. So how do you use this data to sort of come to conclusions? When we found the proof of the Higgs boson, or evidence for the Higgs boson, to put it a little better, less legal terms, right? You had to analyze these mass amounts of data. So this idea of big data has led to the idea of computational approaches, especially in the context of machine learning, where we have programs or machines which are able to learn conclusions that they should come up with rather than being pre-programmed by us about it. So the last 3 chapters of the book sort of deal with this idea, and I end the book with sort of an exploration of machine learning and also applying it to data science, talking about data science, whether that's an actual science or not. This ties into research that I do. I do like fact-checking misinformation and virtual communities and multimedia analyses and digital humanities. And also I do like physics-based models of computer vision. And so the next book that we're doing is about fact-checking misinformation. It applies a lot of these ideas. And so the book sort of takes this thing of going from what's the essence of science, prediction, great. One of the ways that we can think about majority of the math in there is in information theory and entropy, build up the basics of programming, and then end with sort of tying entropy back to these ideas of machine learning and big data and data science. So that's the book in a nutshell. Now you don't need to go read it. And sort of, especially in the context of machine learning, permeates a lot of it. AI, I guess you can sort of break down into more general and narrow AI. So like in the early days being like, as von Neumann and Turing would have like conversations about this back in the 30s and 40s, and they would try and talk about things. These digital machines didn't even exist yet, but they were starting to already wrestle with the idea, could machines replicate human behavior and thought? And so that's the idea of AI. And so I guess we're a very optimistic bunch. So we've always been saying since about 45 or so, in 10 years, we're going to get AI. And every 10 years, we revise that to 10 more years and we'll have it. And eventually around like the 60s or 70s, people started to get a little more realistic and said, okay, it ain't coming. Let's sort of bring our expectations down a bit. So rather than trying to replicate all of human behavior and consciousness and thinking, let's just have machines or programs that can learn certain tasks and become better at it. So that approach, that more narrow approach, ended up being a lot more effective. And so that permeates a lot of the things that you see and utilize every day. And about 10 years ago, there was an interesting sort of transformation. My background's neurobiology. There was another guy that was in computer science, much smarter than me, also neurobiology background, and started to think neural networks had been around for a while because neurons are kind of easy to replicate. You get a little perceptron, you kind of talk about it, you're okay, that's easy. Then people started to build networks with them, and it was okay, but it didn't go anywhere until about 10, 12 years ago. Computing power was at a certain place, and this guy, Jan LeCun, started to look at how neural networks work in vision, especially, and he started to replicate that idea, and these deep neural networks now are crazy. So all the stuff you see with deep fakes and like voice recognition, you might remember like 10 years ago when you called up some system, you'd have to say, please give me your social security number. And you'd say, blah, blah, blah. And you say, please say yes if you want to do this or no. And that was the extent of the interaction. And now you've got Siri, Alexa, Google, and you can interact with them normally. A lot of that advance is because of these neural networks. And these neural networks are going a little nuts. And they're also giving us some insight now into this more general problem of AI. So I'd say AI, pervasive in the sense of machine learning, that's just about everywhere. That benefits almost any field in any organization and any business. General AI, in 10 years, we'll have it.